All right, so I think we've got everything ready here. The last two lectures were pre-recorded on beam deflection, so hopefully you watched those. They were listed in Moodle. I don't think I put them in this playlist though, so if you're only looking at the playlist, you have to find them outside of the playlist. Um, Really, today we're just going to do exam review stuff. So review of frames and machines, review of beams, moments of inertia. Um, Beam deflection is not on exam 2, so we're not going to review that today. Design of beams will be on exam 2. Those are the major topics: frames, machines, um, beams with moments of inertia, beam stress, and design of beams, not beam deflection. So we'll kind of review that stuff. Let's look over here so we can kind of make sure that we're on the same page with everything. We're down here on class 20. So there's only 30 classes. Well, actually, I stopped numbering them. But there's 30 classes, or no, I just numbered them differently because they have specific dates. 30 classes, so we're 2/3 of the way done, which is about how this course works out. 1/3, exam 1 is all the axial stuff. The middle third for exam 2 is the flexural stuff. And then the last third is torsional and other topics mixed in. And that's exam 3. So we're up here at quiz 4 opening. Oh, also, we had power outages yesterday, and quiz 3 could not be completed by some of you because the servers that were serving quiz 3 were down. So I've added some time to quiz 3, so if you need to go back and do quiz 3, you can do that. It's open, I think, until the 20th is when I made it open. I guess I could look at it and see. Let's see, where's it even at? It's hard to find. There it is. I set it until, July 20th. So it's open again if you didn't get a chance to finish it. Looks like only roughly half the people were able to finish it. So that'll open, or that is back open. The web work also would have had trouble, but it was already set to close on the 20th, so it's still open. You just might have lost some time working on it. Today we'll do exam prep for exam 2. Quiz 4 does open. It is going to close, I don't know, it closes, when did I set it? The 24th, so after exam 2. On Wednesday, just like we did lab 1, I have not checked how lab 1 went. Let's see if we've gotten people turning in lab 1. But not yet. So need to get lab 1 done. You got a couple of days to do that. It is SolidWorks. That would have also, I might add some days to that, in fact, because SolidWorks was probably not able, unless you had checked out a license already, which I don't even know if you knew you could do, then you might have had trouble actually using SolidWorks. So let's set that to, does it not have it had a due date, but I'm not seeing it now. Oh, it's down here. Let's add a couple more days to that. Well, it's actually no sense in making it Saturday at midnight. Let's do Sunday at midnight. All right, so in case you had issues with lab 1 and SolidWorks not being available, you've got some more time to work on that. We will start lab 2. Lab 2 will be similar in the sense that it's SolidWorks, and we're doing a simulation of a lab that we would do physically if we were in person on campus. Then we would go and actually go to the machine and test these materials. But since we're not, we're going to do a simulation. Again, these simulations that we're doing, they don't really give you any new information because we have to plug in the information we would normally get from the lab. We have to plug that in for the simulation to run. So they're more so you can see the types of things that you would do in person and get some experience with the simulation part of SolidWorks. All right, so that's coming up. And then Thursday, there was a tiny bit of confusion if the exam was on the 20th or the 21st. It is, let me make sure that's the right day. Where's me a calendar? The 20th, I believe, is the correct day. but there was one place where it said the 21st. That was left over from last year, I believe. Where's my calendar? There it is. Let's see. So I'm hoping that these are the right days. Yes, 20th is Thursday. So it is on the 20th. I do plan to do the two different Zoom. So if you want to do it at noon, then we'll be in Zoom and you can log into Moodle, log into Zoom, take the exam then. Or if you would rather do the 7 o'clock, same day, the 20th, 7 p.m., then same process. You'll log into Zoom, log into Moodle at 7 p.m., do the exam, and that will both of those will be monitored by me. If you need outside of those two, so if you need, Thursday just doesn't work at all, that's when you'll have to set up a proctor. And I know some people have like a library set up. Some people are doing, I need to know if people are doing Proctor U, because that needs to be set up. So that's exam 2. Let me make sure. Yeah, there's nothing in the chat right now. The sound was in my previous class today. The sound was off. So if there's something wrong with the sound, let me know. I think I fixed it. It wasn't off as in not making sound. It was not correct. So actually it did go off for a little while. So if something happens with the sound, let me know so I can fix it. I will try to look at the chat every now and then to make sure I'm paying attention. The YouTube chat. All right. Let's jump in to reviewing for exam 2. I think the best way to do that is, first of all, let's talk about some of the topics that you will be asked for exam 2. So the topic there, it's the same format where there are a certain number of content-related questions. Just a concept that we covered or a definition, something like that. There's some number of those, and there are about, let's see, 2, 4, 6, 8. Actually, that one would count, so that's 14. There's about 10 to 14 points, not questions, points, related to just concepts that we've covered. Again, the main topics for exam 2. Make sure, yeah, that's on the screen. The main topics are frames and machines. I'm not going to separate those. You will have some that are frames and some that are machines, but as far as solving the problem, you're not going to be asked, is this a frame or is this a machine? I guess I could do that, but that's not any of the questions. The questions are calculations based on whatever the diagram is. So frames and machines, which means that you will have to do 2 force members. There might be even some questions about 2 force members, identifying them. Certainly some of the frames or machines, when you solve them, you might have to know how to identify a 2 force member and what it means to be a 2 force member. Remember, lots of members in there. Here's our generic non-2 force member. Maybe it's got a force that's applied over here, so it's not a 2 force member. And when you have that, you have to deal with all of these reactions just like they're pin reactions. Those black dots are pins in my diagram here. So that would not be a 2 force member. But if you do have a 2 force member, then instead of having the pin reactions, you can just have the member reaction, where you connect the 2 pins like with a line, and that line, the dotted line that I drew, is the line of action for the force in that member. So instead of 4 unknowns, AX, AY, BX, and BY, that I have in the left-hand picture, I just have 1 unknown, F. It's just the force in this member, or the tension in this member, or whatever you want to call it. You don't necessarily know if it's tension or compression, you just know it's on that line of action. So identifying 2 force members is very useful, sometimes necessary. for solving these frames and machines. So you need to know about two force members. You might need to know about distributed loads. Now that we can have loads directly on the member, when we were doing frames and machines, the loads all had to be like at a joint somewhere, so like a point load. But now that we're doing frames or machines, the load can be applied to the member itself, like I drew here with this load. It's just a point load on the side. Well, you could have loads that are distributed. Instead of a single point, they're spread out over some area. And the things you might have to do with distributed loads are you might have to lump them. So you might have to lump them into an equivalent point load. That would be, say you've got a beam and it has a distributed load across it. You might have to go in, and if you're calculating a, maybe you're calculating a reaction, you know, you have to write a moment equation or something like that. You might have to go in and lump that distributed load so you can make that calculation, something like that. So you might have to do that. You might have to do that for a whole set of loads, like you've got a whole bunch of distributed loads and you've got to find the equivalent point load, lumped load, the purple one here, for that whole set. You might have to do that. You need to be able to draw shear and bending diagrams with lumped loads and point loads and concentrated moments. I might even put this separately later on. But you need to know how to do distributed loads in a shear and bending diagram setup. Let me see what else might be. I'm looking at my notes. Oh, this is a, it's on all the exams, and I guess I didn't specifically tell you that, but not distributed load, but in general, you need to be able to label a stress strain diagram. Oops, that should be an A. That's this picture. So that thing, you need to be able to label the various points on that, like ultimate strength, yield strength, stress axis, strain axis, elastic region, plastic region, fracture, toughness, strain at fracture, those kind of things. You won't have to label all of those, but some subset of those you'll have to label. Okay, what else do you have to, where are we at? Frames and machines, we're still under frames and machines. Actually, all of the topics are under frames and machines, I think. Another thing you might have to do related to frames and machines, but not directly to the beam part of it, is calculate moments of inertia. So, there's two ways we did that. One was we just looked it up in a chart, in a beam chart. So that's one thing. If you have a S10 by 4 and it's just a beam that you have the name of, you go to your reference sheets and just find the moment of inertia. So you need to be able to do that. Then the other thing is we calculated, where we had a table or a chart of generic, like primitive shapes, rectangles, triangles, circles, quarter circles, and we had the moment of inertia equations for those shapes, and then we could calculate the moment of inertia for some composite shape out of those primitive shapes. So those two things you might have to do. You don't have to draw shear and bending diagrams. because I don't really have a way to do that without a paper-based test. So you don't have to draw them, but you might have to recognize them. Like you might have a beam with some loads on it, and then the multiple choices, are a bunch of different diagrams that could be the shear diagram or the bending diagram for that particular beam, and you have to select the correct one. You don't necessarily have to draw it out and match it up. You can usually, or actually always, you can tell the correct one based on, oh, if there's a point load here, then the shear diagram should have a step change in it. If there's a concentrated moment, then the moment diagram should have a step change. If there's a distributed load, then there should be this gradual change in the shear, and so forth. So, assuming you know the basic rules, remember we wrote a series of if-then statements for shear and bending. Assuming you know how those work, then you don't have to draw the diagram. You can just identify the correct one, like a multiple choice problem. You might have to do some direct calculations. Direct calc of M. So you're given a beam, and it has some series of loads on it. And the question is related to that would be, find M at X feet from the left end. So you would go over X feet, 6 feet, or whatever it says, chop the beam open at that point, and draw your free body diagram. Something like this. There'd be a reaction over here, I guess. And you would find that value for M. X wouldn't be a variable, though. It would be 6 feet or 3 feet or 4 feet or something like that. So there will be some where that's the whole problem. Just find the moment at a certain spot. You could also do that by drawing a shear and bending diagram, but that's going to take you a long time, and you probably don't have that kind of time to spend on that problem. It's meant to be solved this way. There'll be definitely some where you're just given a frame or a machine, it's got some loads, and you find a force in a member somewhere. Here's a little bit more complicated one. Remember, there's two things that will speed up some calculations when you're trying to find M max. So the maximum bending moment in a beam. You might want to find that because you want to find the maximum flexural stress in a beam. So you need to know where the maximum bending moment is. One thing you can do, draw the shear and bending diagram. You can do that. None of the, well, let's see. It is probably not true that you need to do that on the exam 2. There's probably a better way to do it for exam 2. I can't say for certain whether or not that you do not have to draw a shear and bending diagram, but you probably do not. There's probably a different way to do it. So the other ways to do this to find out where's the maximum bending moment is if it's a cantilever beam. So that's the beam, like this, and there's some kind of load on it. M max is right here. So if you have a cantilever beam, then it's, well, and I keep writing wall, but it's really at the fixed support. because you could have this, you know, it could be turned this way possibly, and there's some kind of load on it here. M max would still be up here at the fixed support. So it's not necessarily always a wall. It could be the floor, the ceiling, a beam, another beam that's bolted to, whatever. So it's at the fixed support. So if you have a cantilever beam, that makes it much simpler. You just find the moment at the wall. You don't have to draw the whole shear and bending diagram. If it's simply supported, then there still might be a faster way. So simply supported beam, as long as the supports are symmetric, and the loads are symmetric. So maybe we have a load right in the middle. If we have a distributed load over here, we have one matching it over here. Whoops. So as long as everything is symmetric, then you know you've got this line of symmetry right through the middle. As long as all that's true, then the M max is at, well, not equal to, it's at L over 2. Can't write an at symbol all of a sudden. There we go. L being the length of the beam. Or the length of the span, rather. Which, for it to be symmetric, would also be the length of the beam. Or at least it would be the same point. I guess the beam could overhang some. Alright, so, and if it's not one of those cases, then the only way to find M max is drawing the shear and bending diagram. But that's probably not what I'm asking you to do on this little exam. I don't know. This is possible. I don't know if it's on the exam or not, if I'll put it on there. But most of the time, unless you're specifically told to do this, the assumption is you're going to ignore the self-weight. I know there's one web work problem where you don't ignore the self-weight, but unless you're specifically told to consider it, then the assumption is you're going to ignore it. If you are told to consider the self-weight of the beam, then there's something given in the problem statement that tells you what that weight is. Either just tells you the beam weighs this much. Probably what it is, well, let's use two different, no, 10 by 8. Probably it is a particular beam that you have a designation for, and this number is the weight of the beam per unit length. So this, and you have to look in the chart at the bottom of the charts to see what the units are, because it could be kilograms per millimeter or millimeter or something, or it could be pounds per foot or whatever. So you have to look at the bottom of the chart to see what the units are. And then kilograms aren't an actual weight. You have to convert that over to a force to make any calculations with it. But most of the time you just ignore this. Unless you're specifically told to consider the self-weight of the beam, you're going to ignore it. And some problems will actually tell you to ignore the self-weight of the beam. But if they don't say anything, the assumption is you're going to ignore it. Let's see. I think that's You will have some, obviously, where you find flexural stress. So that's sigma equals negative m times y over I. A few little things with this. It could be that you've got to find the maximum flexural stress. So that would mean you'd need to know the maximum bending moment. So you might be given a shear and bending diagram and you have to find M max off of it. Basically just look it up off of the picture. Another potential complication is if the beam is not an I-beam, I've drawn a T here, then you have two different flexural stresses. One of them that's measured to the top of the beam with one value for y, and another that's measured at the bottom of the beam and a different value for y. So the y2 that I've drawn here is a larger number, it's a bigger distance than y1. So if I just want to know the maximum flexural stress, I'm going to have to use y2 in my flexural stress equation. Another thing you might be given is find the maximum tensile flexural stress or compressive flexural stress. So it might specify tension or compression. In that case, you need to know, well, is tension on the top of the beam or the bottom of the beam? So how you tell that is if that bending moment is greater than 0, I guess I shouldn't put equal, I should put greater. If it is 0, then there's no flexural stress. But if it's greater than 0, so it's a positive bending moment, then the beam has tension on the bottom and compression on the top. If M is less than 0, so it's a negative number, then you've got tension on the top of the beam and compression on the bottom. So you can tell if the tension's on the top of the beam or the bottom of the beam, whether or not M is positive or negative. So not including this minus sign that's just part of the equation. So not including that, just M itself. So you're looking at the shear and bending diagram, or you're just given M equals. If it's positive, then the tension's on the bottom. And if it's negative, the tension's on the top. Remember that this is easy to remember because positive moments make the smiley face and negative moments make the frowny face. So you can always remember, you won't forget that. What else? Covered all those, yeah. Oh, I can confirm that there is one problem on exam 2 where you are specifically told to consider the self-weight of the beam. So that means look at that second number, and that is the weight. You just have to know what the units are. So if the units are set up as kips and feet and stuff like that, then that is pounds per foot. And if it's set up as millimeters and kilograms and that thing, it's kilograms per, I believe it's kilograms per meter. You'd have to look at the chart to see what it actually is. But anyway, so that's an overview of the variety of topics that you will have to cover in exam 2. Did I write down? You have to you have to calculate moments of inertia. So I did write that down. And there will be some where you just look up the moment of inertia as part of a bigger problem. Okay, so that's the broadness of the topics that you'll have for exam 2. So it's not too bad. It's all beam related one way or another, flexural stress related at least, and then the other topic in there is moments of inertia, which you need to calculate flexural stress. But there is no, I will even write that down, no beam deflection on exam 2. Those, well, for one thing, those are the ones I had to give you a pre-recorded video for. You do have some web work, homeworks that are beam deflection, but they're not on exam 2. There might be one on exam 3, but they're just too recent for them to be on exam 2. All right, let's work a problem or two. If you have a particular one that you want to see, I don't know if I worked the whole thing or not, but at least set up, then put it in the chat. Otherwise, I'm going to grab something from WebWork that looks like a reasonable one to work on. So I guess I should log into WebWork. I'll get some out of optional 2. And let's just go through them. And some of these we've already worked. It wouldn't hurt to work on them again, I suppose, but I don't want to do one that I don't think we did this one. This one might be worth looking at. That's a frame, just a general frame problem. So, got this. So we've got this one on the screen there. Should we make it bigger? There we go. So we've got this crane looking thing holding up a rock. You know, a crane normally is a machine of some sort, but the way this is drawn, it's going to be a frame. It does give us a couple of little hints here, rigidly attached. So down here at F, that's one of our fixed supports. So it's going to have the 3 reactions, the X, Y, and a concentrated moment there. There's a cable at D. Okay, there's a cable at D. This is, let's see, that the same cable passes over frictionless pulleys at A and E. So this is all one cable here, over there, around there, and down to the ground. That's all one cable, and they're all frictionless pulleys. So what that means is that that tension in that cable does not change. It's all the same tension anywhere in that cable. The object, so the rock, has a mass. Oh, all right. So it is a mass, not a force. So we do have to convert this over to a force, 1,330 kilograms. So we need to multiply times 9.81 meters per sec. Whoops, that's 3 meters per second squared to get an actual force from it. So what is that? 1,330 times 9.8 times 9. Well, times 9.81. 13.047 kilonewtons. Some of these web work problems are whenever they give you a kilogram that you have to convert to a newton. Sometimes they're set up to use 9.8 millimeters per second squared, and sometimes they're set up 9.81. So if you're knowing you're doing everything correct and you're still getting the wrong answer, try the other. So if you tried 9.81, then try 9.8 and see if it works that way. I don't know why some are one way and some are another way. That's the way they were coded by different people and probably just used a different value. We have some dimensions here, and what we're supposed to find are the forces acting on A, B, C, D, reaction at F, shear stress on a cross section of a pin at A over there on the left hand side, blah blah blah. It has double shear, all that kind of stuff. So if we draw let's draw the whole free body diagram. Let's look for 2 force members. The cables are 2 force members, but other than that, there are not 2 force members. So let's just draw our free body diagram of the whole thing, because it is a frame, and normally when you have frames, the first thing to do is find the external reactions. That's B. All right, and we have a cable over here. So we don't know this force, but there is a tension in the cable. We do know this force. It is the weight of the rock, 13.0, let's just call it 0.5. Web work will probably not like that. Kilonewtons. And then at F, we have a vertical force that keeps the whole thing up, a horizontal force that keeps it from moving left and right, and then a concentrated moment, we'll call that the moment at F, that keeps it from tilting over. So those three reactions are at all the fixed supports, X, Y, and a moment. So if I look at this, I have four unknowns. I have Fx, Fy, the moment at F, and the tension in the cable. So I know I can't solve for all of them. I only have three equilibrium equations. I can look and see that Fx is 0 because it's the only one in the X direction. So I can do that. And I can see that tension in the cable equals the force in Y plus tension, or the 13 kilonewtons, or minus. But I can't solve for it. And I can write an equation for the moment at F, but I can't solve for it. So there's got to be something else going on with this problem. So if you get to this point, even though the little flowchart algorithm type thing that I said is, when you have a frame, first thing to do is find the external reaction. Sometimes you get there and you can't do that. Like we solved for f of x just by observation, really. But we can't solve for anything else. So the first thing to do when you get there is look for two force members, because maybe you missed a two force member and you don't really have fx and fy, you just have f. That's not the case here. So that's not going to help us. So if you get that bad, you've looked for all the two force members, you've drawn your free body diagram of everything, and you still have too many unknowns, then start taking it apart. And it is usually going to be best to take it apart in a way that you have the piece you're drawing has at least one known value on it. The only value I know is, oh wow, that's hard to see. Let's change that back to yellow. 13 kilonewtons. So that is applied to member ABCD. So I'm going to draw member ABCD, just it, and see if we can get anywhere with that. There's A. B is over here somewhere. C is there, and D is there. Okay. C, we have the 13.05 kilonewtons. D, we had a tension. I'm just going to call them T. I wrote T in the T cable last time, but just to save space, I'm just going to write T. T is the tension in the cable. In fact, we can do that. T equals T cable. Now, that makes it easier to write it out. B is a big giant pin. Big giant pin holding these pieces together. So they're not two force members, so this is just BX and BY. A has two cables coming off of it, one here and one here. So essentially what I did is I took this free body diagram here and cut it out of the picture, unbolted it from B, and this is what it would look like. Now, it would have some dimensions and things like that. Why don't we start putting those in? But here, it looks like I've got a bunch of unknowns. Like there's 1, 2, 3, 4, 5 arrows that don't have values, but 3 of them are all T. So they're all the same. So I really only have 3 unknowns. So I can work with 3 unknowns if it's not a concurrent force system, which it's not. So I can solve these. I just need the dimensions on there to be able to do anything. So let's see what our dimensions are. From A to B is W1, 7 meters. From B to C is W2, 10 meters. And from C to D is W3, 4 meters. Now I need something with these angles. The T at A pointing down is just straight down, but the other two are angled. So H2 is 6 meters. So this has a height of 6 and a run of 7, which gives it a hypotenuse of, let's see, 6 squared plus 7 squared, square root of that number is 9.22. The other one has a height of 6 and a rise of 6 and a run of W2 plus 3, 14. And that gives it a hypotenuse 6 squared plus 14 squared. Square root of that number is 15.23. Or you could go in, if you don't like using the rise over run and using that directly, you could find the angles and use sine and cosine. So if you do inverse tangent of 6 over 14 would give you the angle of the cable at D. So you could do it that way too. But this is everything I need. It does probably help to look and see if there's something that I can do that just solves for anything. And it looks like if I do moments about B, I'll have a bunch of stuff in the equation, but the only unknowns will be T. So I'm going to do that. Actually, let's put that down here because that's probably going to be a long equation. All right. So doing summation of moments about B. The T, I'm going to start at A and work my way to D. So the T that's pointing straight down. So minus T times 7 meters. That one's pretty easy. The T that's at a 6 over 7 angle plus T, I only want the Y component, so that would be 6 over 9.22. Or if you had calculated the angle, then you could do the, well, depending on what angle you had, you could do the sine or cosine. That's times 7 meters. BX and BY, their lines of action intersect point B, so they do not create moments about point B. 13.05 kilonewtons times 10 meter moment arm minus T, I only want the Y component, 6 over 15.23 times a 14 meter moment arm. All of that has to equal 0. I'm only using the Y component here because here's the Y component at D. Here's the X component. Or I did it the other way, didn't I? Oh. Well, that's fine. I wrote the other one YD and this one I wrote DX. But the X component, the horizontal component, its line of action intersects point B, so it doesn't create a moment about point B. So I've got this equation. Let's see what we can do with it. 7. I'm going to leave the meters out and the kilonewtons out just to try and, everything's in meters and kilonewtons. So I'm going to leave that out for now. So minus 7t plus, let's see what this number is. 6 times 7 divided by 9.22 is 4.56t plus 13.05 times 10, well, I guess that's 130. That's actually kilonewton meters minus 6 times 14 divided by 15.23, 5.52t equals 0. So now I've got all these t values. So I've got 7 plus 5.52 minus 4.56. I'm moving them to the right side of the equals so that all their signs are flipping. So I've got 130.5 kilonewton meters equals 7.96 times t. 7.96 meters times t. T should equal 130.5 divided by 7.96, 16.39 kilonewtons. Let's see. Oh, do I not have that? I may not have that as an answer I can check. Yeah, I don't have that as an answer I can easily check. So I think we did it right, but I can't check it. Once I know that, then I would go in and I'm not going to write these out just so we can move on from the problem. Summation of forces in x direction would give me bx, and then summation of forces in the y direction would give me by. And I'd have all the unknowns on that piece. Actually, I'd have I would still have to know fx, fy, and mf, but I could take this value of t that I just found, I could take it and apply it to, can't do that. All right, and I could apply it to this free body diagram here, and I'm back to just having two unknowns, fy, mf. I've already solved for f of x, so I could solve this now. I could figure out fy with summation of forces in the y direction. I could find mf by summation of moments about m, or about f. Okay. Don't see any chat questions, so I'm going to carry on. Let's go back and see what else we have. That was, oh, I don't remember what number that was. That was optional 2, problem 3. We worked on that one already, problem 4. This is the problem. So let me show you this one real quick, just so you know that we're not doing this. These style, where you've got to develop an equation, and the answer is the equation. We're not doing any of those on exam 2, but you might have one where you have to go to a particular spot in the beam and use an equation like this, but you don't have to develop the parametric equations. Okay. Same thing here. These where you're trying to draw a shear and bending diagram in, all these blocks and everything. We're not doing that on exam 2. That's just a harder version. You will have something like this. This is a really simple one, where you're calculating the couple of things. You're calculating flexural stress, but you also have to find the moment of inertia for this half circle. This one's probably a little too simple compared to the test question. So the test question like this would have at least 2 pieces. So you'd have to do a composite moment of inertia. We could do this one. This one's not bad. All right, this one has a beam with a cross section shown like this. This is not too far from the truth. I don't have a handy piece, but well, actually, right here. Well, not this one, but sort of like this one. There can be aluminum extrusions that have cross sections that are not too far from this kind of shape, where they're some kind of extrusion with a hole through the middle of it. So this is kind of a realistic beam. very simplified though. But we have this beam. This is the cross section. This one gives us a little bit different piece of information. It gives us a sigma max. So it's just telling us this is the maximum stress that can exist on this beam. We want to find the maximum bending moment that we could put on this beam given those dimensions so that we don't exceed this. So remember, sigma equals negative m times y over I. So 128 megapascals will go in for sigma. Y, so looking at this beam, the neutral axis is going to be right through the center of it. I can tell just by the way it's shaped. It's all symmetric. So even though it has a hole through the middle, the hole is symmetric also. So the neutral axis is right in the middle, which means that Y is going to be measured from the neutral axis to the top of the beam, which is A, or neutral axis to the bottom of the beam, which is also A. So either way, A goes in for Y, and we just have to develop an equation or calculate the moment of inertia and then solve for M. So this one doesn't need the fancy thing, doesn't need parallel axis theorem, because the centroid for the circle and the centroid for the square, this is a square, both of those, their centroids are already sitting right on top of the neutral axis, so they don't need to be moved to a parallel axis. They're already at the neutral axis. We do need to get our charts. Let's go see if I can find a chart that we can use. I'm just going to get the one. You do have exam reference 1 and exam reference 2 that you can use on exam 2, so you might want to print those out or have them where you can look at them. I'm going to get moments of it. I'm going to get this chart. All right, so there's this. This picture shows a rectangle, and it shows the moment of inertia about x, which is already at the centroid. Actually, let's just copy these so we can write on them. Copy that. And let's copy, we need a circle too. All right, so now we're back over here. So, here's the centroid of the rectangle, but would also be a square too. That label is x, which matches up with this equation. So the equation for the square or rectangle for the moment of inertia about the x-axis, which is at the centroid, is bh cubed over 12. And b is the base, h is the height. They're both a, well actually they're both 2a in our picture here. So the moment of inertia for the whole shape equals the moment of inertia for the square minus the moment of inertia for the circle, since the circle is cut away from it. So for the square, base is 2a, b, height is 2a, bh cubed over 12. So whatever a is, we'll have to plug that in. A is 26 millimeters for me. Minus the moment of inertia of the circle about the neutral axis, which happens to also be the circle's centroid. So again, we're at this axis, which is x, which corresponds to that equation. The other one, the x, I don't know if you can tell on here. It's probably small depending on what you're watching on. But this one is x prime, which corresponds to the moment of inertia of the circle about the tangent line at the bottom. That is not what we want. We want the moment of inertia of the circle about the centroid of the circle. And the centroid is already at the neutral axis of our composite shape. So we don't want that one. So it's pi r to the fourth over 4. So minus pi, r is capital R, over 4. So our numbers equals 2a, so 52 millimeters times 52 millimeters cubed over 12 minus pi, r is 9 millimeters to the fourth over 4. See what that equals. So it's really 52 to the fourth in my numerator. So a giant number divided by 12. Still a big number. 609,301.3 millimeters to the fourth minus 9 to the fourth times pi divided by 4, 153. So that math, 609,301.3 minus 5153. The total moment of inertia for the composite, 604,148.3 millimeters to the fourth power. That can go in here. The only unknown now is m, which is what we want to find. So 128 times 10 to the 6 newtons per meter squared, that's Pascal, megapascals when we did the 10 to the 6, equals negative m times y, which is 26 millimeters. I've got meters everywhere else, so let's convert that to meters also. 0.026 meters over I, so 604,148.3 millimeters to the fourth. We have to convert that to meters to the fourth, so that's divided by 1,004 times. Makes it a super tiny number. 0.12345 604 meters to the fourth. Now everything should cancel out, and we can solve for m. So 128 million times that really small number, divided by 0.026, I get m, and technically I get a negative number, but it won't matter if I apply a positive moment or a negative moment. It'll still be the largest magnitude of moment that can be applied. So m of 2,973.54, and my units would be Newton meters. So 2.97 kilonewton meters. Hopefully WebWork likes that number. 2.974, yes. I put 2.9735, so yes, it would like that, I think, if I plugged it in. So that one's a little bit of a design type problem, where you're solving for the moment instead of the flexural stress. But I don't know that you have a design problem on exam 2. Actually, you might. There is. I did forget to write one topic in here, didn't I? Let's see. Design of beams. Which involves the section modulus. So you, instead of designing the beam, you're calculating the necessary section modulus, and then of the beams available to you, which in your exam will just be a list of beams, multiple choice list. of those beams, which one is the one that has the necessary section modulus, so it has enough, and is the lightest weight of the ones that can support the load. So that would be the correct answer. All right, let's see what else we have in here that might be worth looking at. Let's see. This is probably a good one for you to just solve on your own. It is very straightforward. It is one of the ones where it's asking you for maximum tensile. In this case, it says it's a rectangular cross section, so the tension and compression maxes are the same number. Just one's positive, one's negative. But I think you could do that one on your own. Let's see, are A and C, they are not. So this one is not one that you could quickly solve, except that this is the type of problem where you have a particular section shown, AA, and you're given a location for that section. So you don't have to draw the shear and bending diagram for this one. You can just chop the beam open. This might be a good one to solve. And if there aren't any questions, this might be a good stopping point once we're done with it. So let's work on this one. Okay. Oh, one thing about this one, this one is not the case, but sometimes you do have, this is a steel pipe. So it's a hollow tube. There are, this one just gives you dimensions. Outside diameter and inside diameter is just given. But you also have pipe that is like a nominal size, like 2-inch pipe or 2 1/4 inch pipe or 2 1/2 inch pipe. If you have that kind, or if it says the word nominal diameter or something along those lines, then that means you need to go and find the actual size of the pipe. So in your case, you would go to, I don't remember which exam reference it is, or if you have the book, I don't remember which page number it is, but there is a, here they are, got to rotate. So over here in the right hand corner, properties of, this is standard steel pipe, so PVC pipe would have its own set of table like this. We just don't do anything with that in the class. And you might see a standard weight or extra strong or double extra strong. That talks about how thick the walls are in it. So if it's a standard 2-inch pipe, the outside diameter is actually 2.375 inches. And there's the inside diameter, 2.067. So if you're given something like a standard steel pipe or nominal size pipe, see nominal diameter up here, then you need to go to a chart like this one and find the actual dimensions of it. Here, this one just specifically gives us the dimensions outside and inside, so we don't have to do that. Let's see, I've lost my pen. There it is. All right, so we have it does say it's a steel pipe, but it's not one that we have to look up. Simply supported. It carries 2 loads, has some dimensions, and it wants us to find the flexural stress at point A. So point A means the, it gives us this diagram over here on where point A is. It's not these A's, that's showing the section A. Point A is apparently at the top of this pipe. And then we want to do it again for the inside radius of the pipe and then anywhere in the beam. So the anywhere in the beam part, the C part here, that one would require you to draw a shear and bending diagram, and we're not going to do that. So we're just going to do the chop the beam open at AA and solve for flexural stress. All right. So before we can do that, though, we need to know the reaction at the pin or the roller. So let's just put our dimensions on here and our labels on here. This will be the reaction that looks like it's labeled C, so we'll call it CY. F1 is 780 pounds. F2 is 1760 pounds. And then over here at the roller, I have a dy. Technically, I have a cx, but it's 0. And I have this dimension, A is 2.8 feet. I have this dimension, 13.2 feet. And I have this little dimension, 2.1 feet. Okay, so I'm gonna plan to work on the right hand side just because we don't do that one as much. So I want to do the right hand side, which means I need to know dy. So if I need to know dy, I'm going to solve for summation of moments about c equals 0. So I've got 780 pounds times 2.8 feet plus 1760 pounds times 16 feet minus dy times 18.1 feet equals 0. And we can solve for dy. Okay, let's see, 780 times 2.8 plus 1760 times 16 divided by 18.1, 1,676 point, we'll just call it 5 pounds. Okay. Now I can go to section AA, which is, what did it say, 4.8 feet from here, and draw that free body diagram. So I'm going to cut it open right on that section. So I've got dy, which we just solved, 1676.5 pounds. I've got, maybe right here, 1760 pounds. I've got the internal shear force and the internal bending moment. Since I'm wanting to do flexural stress, I need that internal bending moment. Oh, and I also have some dimensions. I have this dimension at 4.8 feet, which is where they told me to cut section AA, and they also told me this was 2.1 feet. Now we can work on that. So to find the moment at A, we would do, I don't want to move this over, kind of feels weird over there. Summation of moments about our cut, you know, our little cut spot here, equals 0. M is just M plus 1760 pounds. The moment arm there is 4.8 minus 2.1, 2.7 feet, minus the dy, 1676.5 pounds with a 4.8 foot moment arm. V is on that cut surface, so it doesn't create a moment about M, so we can ignore that one, or not ignore it, it just doesn't create a moment. And solve for M. So therefore M equals 1760 times 2.7 minus 1676.5 times 4.8 is a, that number is negative, but then I move it to the other side of the equal sign, it becomes positive. 3,295.2. All of my units are foot-pounds. They don't want that though. They want us to find the stress. So Flexural stress, sigma equals negative m times y over I. So I just found m at section AA. Now I need y and I. Y, if we blow up our cross section here a little bit, so there's our cross section. This one is also symmetric, so we know that the neutral axis just goes right through the center of it. And they gave us some dimensions. They said the outer diameter of 3.9. So OD is outer diameter. They gave us an inner diameter 2.85. So ID is inner diameter. So point A in our little picture is up here. So that means that the Y value in our equation is that distance, which is half of 3.9. So all right, 1.95 inches. So now we have m and y. We just need the moment of inertia. So we can actually go back to this little circle, because all this is a big circle with a little circle subtracted away from it. So moment of inertia about the own centroid, which in this case the centroid of both circles, the outer and inner, is right on top of the neutral axis for the composite shape, so I don't have to use parallel axis theorem. So pi r to the fourth over 4. So I for the composite shape equals pi outer radius, so 3.9 divided by 2, pi r to the fourth over 4 minus pi inner radius, 2.85 divided by 2, 1.425 inches to the fourth over 4. And I can just solve for the total moment of inertia. Let's see, this first number is 11.36. Second number, .23. Let's say I only use 2. Let's do 2.4. So the total number, 8.12 inches to the fourth. And now I should have all the stuff I need for sigma equals negative m times y over I. The negative will tell me that I've got compression or tension. I think I've been keeping up with, I've been keeping up with everything. I have a positive bending moment, which should put compression on the top. 3,295.2. Those are foot pounds, though, so I'm going to convert that over to inch pounds. 12 inches per foot. Y was already in inches, and I was in inches to the fourth. So now my final answer should be in pounds per square inch, which is PSI. And it should be negative. 3295.2 times 12 times 1.95 divided by 8.12 is 9,000, or negative 9,496 PSI. Equals negative 9.5 KSI. Let's see if WebWork agrees. 9498. We had 9496. Close enough. I rounded a couple of places in these decimals here and here, actually a lot in here, so I can be okay with that. All right, so those are the types of things you might have to do on exam 2. This list is relatively complete. We didn't practice a design of beam. We didn't practice one of those. They're pretty straightforward, and there's not a whole lot to do on those other than find the section modulus. So it's relatively straightforward. All right. Work through some of this. On Wednesday, we don't have a review session, but we don't have a new topic either. We have Lab 2. Let's see. Make sure I'm telling you the right thing here. If it'll load up. So Wednesday we have Lab 2 SolidWorks. So that does give plenty of time for questions also. If you have some last minute questions before the exam the following day, then you do have some time to ask them on Wednesday, because most of what I'll do on Wednesday is show you how to do the simulation in SolidWorks. All right, I will see y'all then, and let me know if you have